Many of my students have appreciated how the concepts they're learning in class can be used in concrete applications and examples. So today, I'm going to show you two examples of how the concepts of the gray box, neural networks, and sparse regression may be used in actual applications and examples. I have to thank my PhD student, Sachin Nagela, for helping me generate a lot of the material that you'll see today. The first example, I like to first introduce you to a partial differential equation that is very often studied in science and engineering. It's called the Kuramoto-Sivashinsky equation. It looks like this long and ugly partial differential equation. Let me first break it down by term to explain the physics of what this model represents. First, we have a time derivative of some multivariable function f, which is a function in this case of position x and time. So the left-hand side tells you the accumulation. The first term on the right-hand side here looks kind of like a diffusion term. If you have partial f partial t is equal to the Laplacian of f, that is your normal heat equation or your diffusion equation. That says if I have some pulse in concentration or a steep gradient in your temperature or concentration, diffusion will tend to smooth things out so that everything is a uniform distribution. The only major difference, it's a small difference, but a catastrophically different point, is that this term has a negative sign out in front. This is kind of like having a negative diffusion or a negative viscosity. What this is saying is that if you were to have a uniform distribution of temperature or concentration, any small ripple or a numerical fluctuation in your concentration would have a negative diffusion. So a very small bump in your temperature or concentration would grow and grow and grow as a function of time, and you get a concentration that spikes to infinity. So generally, negative of a Laplacian term is very bad because that means that you have an instability occurring. It is catastrophically unstable because a very, very small perturbation or fluctuation in the system will spontaneously grow exponentially quickly, and your experiment or system or whatever will just explode on you. Therefore, negative diffusion is generally a bad thing. However, in the Kuramoto-Sivashinsky equation, there is an additional term on the right-hand side, which is a fourth order derivative. Now, what's interesting about this fourth order derivative is that this will actually act as a stabilizing force that will actually beat out this negative diffusion term over a large enough wavelength. Therefore, this term will actually be very, very stabilizing, especially at the high frequency modes. So whenever you have some kind of ripple at very, very, very high frequency, the negative diffusion wants to say, oh, I'm going to take that high frequency bumps in your temperature and concentration. I want to make that diverge. I want to make the peaks go taller, the valleys go deeper. But this stabilizing term says, no. I want the high frequency mode. I'm going to stabilize it. And therefore, what you're going to get is a term that tries to create unstable modes, but a stabilizing term that says, nope, I'm going to just stabilize those and just have this system not explode on us. And so what you end up getting is that some modes that are small modes or small frequencies that will start to diverge, but then the high frequency modes that are stabilized. So you have certain frequencies that are unstable, larger frequencies that are stable. Okay, so it's an interesting system. Now, the last term is this term over here on the right. This is a nonlinear term. This term is a partial derivative with respect to x of f squared. This term represents shocks. You often find this in wave equations or nonlinear wave equations. For example, with traffic. Whenever you have cars on the road, you're driving and there's a bunch of cars everywhere, and you're driving, and boom, you hit traffic, and then you get a shock wave that actually penetrates and permeates behind you. And therefore, there is a shock that kind of happens and is very commonly used to explain traffic, queuing theory. When you go to a theme park, there's a lot of shocks happening everywhere. And so this is a term that's often modeled in those kind of situations as well. So let me show you the solution of what the combination of all of these terms look like. Now, this nonlinear term does actually a lot of interesting things because, like I said, this negative diffusion is unstable over a range of frequencies, whereas this term is stabilizing over the higher frequencies. And therefore, this shock term is a nonlinear term that can actually couple different modes together. Whenever you have nonlinear terms in a partial differential equations, if you were to put it in a sine wave of a particular frequency, that can couple to higher frequencies or lower frequencies. So it's a term that can convert freely between the different modes in your system. So now you have an interesting combination of three terms where one term will tend to shuffle across the different modes, one term that says I'm going to be stable over some of those modes, and a last term that says, oh, I'm going to be very unstable over other of those modes. So what's this dynamic actually look like? Over here, I'm going to plot the function f as a function of position x, and the colors are the instantaneous solutions of this partial differential equation, and you can see it time evolving. So you're seeing an animation of a time evolution of this equation starting from a uniform distribution with a little bit of noise. So I'm going to play this again. So we're going to see is that the modes initially quickly grow because of this negative diffusion term, but then it's just stabilizing enough. And this shock nonlinear term is actually causing these fronts to migrate and diffuse and spread like a wave. So you get a dynamic that looks something like this. And you can see that there's a lot going on. You see these peaks trying to grow, but they're being stabilized over a certain wavelength of the peak to peaks and the valley to valley. And you can see these migrations of these fronts that collide into each other and crash. And this is an example of a chaotic partial differential equation. This equation has no noise in it, but you can see in the solution that it looks like there's a lot of noise, but there's actually no noise in it. And the reason why you see these ripples and this chaotic motion is purely due to this nonlinear term. You're seeing shock waves propagate across the system. Now, let's suppose that I had access to this data. So you take your measurements of f and you store that into a gigantic matrix. Now you can see how this might come back to the stuff we're learning in class. Suppose you have measurements of f as a function of position and time. You have a gigantic matrix that contains your measurement of f. Now, suppose that I wanted to learn an equation that looks something like this, but suppose that you didn't quite know the full equation. Suppose that you knew most of the terms, but one of the term, for example, the nonlinear term, you had no idea about. This is similar to the reaction diffusion system that we talked about in multiple of these lecture series, where you didn't know what the unknown source term was. Similar to that, in this case, we don't know what this nonlinear term or potentially nonlinear term looks like. This term v is some function of f, unknown. And we want to ask, can we just use information that we've collected from our experimental measurements alone to figure out what this v function might be? So once again, we're putting mathematical structure. For example, we're putting a negative diffusion, we're putting in a positive stabilizing term with the physical insight that those terms are required to explain the dynamics of these chaotic migrating fronts. Oh, and by the way, this type of equation, the Kuramoto-Sivashinsky equation, is very commonly used to describe interfacial phenomena. If you have this is maybe a bad example to use, but a forest fire happening along a mountain. You see these interfaces of burned areas and unburned areas, and it looks like a chaotic interface with ripples that kind of show you the interface between the unburned sections and the burned sections. So the interface of a migration is often used to describe this kind of problem. Or any kind of interfacial phenomena like heterogeneous catalysis might also be used to explain shocks and problems like this. And so it's a very commonly used model to explain a lot of problems that have a complicated interfacial phenomena that has a lot of ripples, coupling of modes. It's very commonly studied as a toy example, and actually as a real model too. So back to our example, can we use the interfacial fluctuation in the data alone to figure out the nonlinear term? Now, what we can do is use the lecture that we've covered on the gray box model, where we can assume some sort of orthogonal basis model for this unknown function v. Now suppose that we wanted to expand this function as a sum of a bunch of Legendre polynomials, which is an orthogonal basis function. Just like sines, cosines, Bessel's functions, they're orthogonal, and you can span the entire function space by adding together a bunch of these Legendre polynomials with their proper weights a sub n. So now, if we can model whatever this unknown function is using the Legendre basis and know the weights, then maybe we can figure out the mechanism of what this unknown function might be. Now, what we can do then is to, again, be inspired by our gray box modeling, where we can penalize using the raw data that you've collected by solving this equation to get your predicted function that I'm calling u. Okay, that's our u prediction. And this first term will subtract your predicted solution from the actual truth. So this will be your true data set, u truth. And the mean squared error of that will give you the data loss. That's how wrong is your predicted solution for the interfacial fluctuation compared to the real fluctuation. And you can add other penalty terms like we also described during the lectures. For example, you can put a penalty for how quickly your profile is changing as a function of time. In this particular example, it's very smart to include a time penalty like this because, as I said in the lecture, whenever you have rapidly propagating dynamics like crashing waves and propagation and merging and rare fractions and shocks, the time dynamics become very important. So including a penalty on how quickly your profile is changing in time seems like a very intelligent thing to do. Lastly, because we don't want to make sure we don't overfit the Legendre polynomial using all the basis functions, we're going to add a sparsity term to make sure that we pick out only the minimal number of coefficients a sub n that's required to completely model this unknown function v. All right, so maybe I can draw a block diagram of the gray box that puts in the structure of what we're doing here, and I think you'll see how the problem we're working out here maps on to what we've already covered with the gray box lecture. It would look something like this, where we have some inputs, x and time, coming through. We would impose the mathematical structure based upon our physical intuition that it must be obeyed by this governing equation, except there's a term v as some function of f that we don't know. In the previous example, that was the chemical rate equation. We didn't know the rate law. In this case, we don't know what v is, and we put it inside of a position derivative. Now, lastly, we've expanded that unknown function v as a Fourier series of the Legendre basis functions p sub n, and we don't know what the weights are, a sub n. Therefore, we're going to solve this PDE under some guess of an initial weight. It's going to solve this partial differential equation so that we have a predicted f that comes out. And we're going to siphon off that solution, compare with the loss based upon the true data set that we're feeding in, plus the sparsity term. So we're going to minimize these three penalty terms, and then we're going to update the neural network based upon the auto differentiation. Last time I showed you a Python script where there were those three magical lines that can go down and ski down the Swiss Alps, go down the gradient descents, and auto differentiate, update all the neural network weights that will give me a better prediction of the Fourier weights A sub n. So once again, in this particular case, what we're doing is we're taking the predicted value of the function f, and it's spitting out the weights, A sub n, and that's what the black box is doing. Notice that once again, it all comes down to the creativity of how you're using the black box element. In this particular case, the black box is just mapping from function to the Fourier weights A sub n. Once we have the weights, boom, we're done, because we slap it on with the Legendre orthogonal basis function, we know our v, and then we can solve this PDE. So this element that I've circled in yellow or green or whatever this color is the PDE solver. So in this scheme, we're actually solving a partial differential equation. And we're getting an output, minimizing this loss. Hopefully, we'll converge to some balance of the coefficients A sub n with, of course, this sparsity term, this parsimonious term mixed in there, because I'm stingy. I want the stingiest possible model that will tell me only the weights of the Legendre polynomial that are essential for minimizing the data loss and other loss terms that we put in here. And finally, out comes the function f. And hopefully, if the neural network learned the right weights to take, we'll have a complete partial differential equation that then we can then use to analyze this function v and make it interpretable so we can look at the mechanism. So everything I've outlined in blue, that would be the gray box. And as you can see, some aspects of the gray box are transparent. We can see right through the box and look at each of the physical terms that we put in there because we have the mathematical structure. But other parts are completely dark. They're opaque. We can't see. This neural network, we have no idea what's happening inside of there. That's why it's a mixture of both the white box aspects, so we know the terms, we know the physics based upon our insight and intuition, plus some aspects of the black box that we can't see. Therefore, it's gray. And hopefully you're getting a sense at this stage that this grayness can slide from all the way to the white box, all the way to the black box. So you can play around with the different structures and neural networks that you put into this architecture so that the grayness will change. For this particular example, I've chosen this architecture. Like I said, 80% of the problem is setting up this architecture. Once you have this architecture, it's just details. It's just the details of coding it up, and hopefully it works out. If it doesn't, you change your architecture and see if you have better luck. All right, let me show you the actual outcome of performing this gray box on the data that I showed you. We're going to use a subset of the full data set as the training data. I'm going to withhold some of the data, and we're going to compare the prediction based upon the model we converge to in the actual data set. So we're going to compare the withheld data as a control to see how good our model converged. All right, let's look at that next. All right, what I'm showing you here is after the training process, after doing that whole loop, the training cycle on the training part of the data set, we're going to compare the converged model based upon the neural network, V, that hopefully it found the right weights for the Legendre polynomial. Now we're going to put that into our PDE, and we're going to now solve this PDE as if we have the completed model. That's what's shown in the yellow curve right here. That's our prediction based upon the neural network converged or trained value for this unknown function. And the cyan dashed line is the truth. I'm using withheld data that were not a part of the training data set to see if the converged or predicted value of my solution agrees with the actual true data that we withheld. It was not a part of the training data. So you're going to see is, again, the function f as a function of position for different time points. Let's play this movie and see what happens. So what you see is you essentially only see one curve. The yellow curve, which is a prediction, the blue dashed line are spot right on top of each other across the entire spatial domain, but also in time. It's very accurately capturing these rapid, sudden crashes of these different waves that converge towards each other. And it's very good for even these highly curved regions that are crashing into each other. So it gives us a lot of hope and promise that it converged to the right equation, the right PD at the very end. Now, as a comparison, what I'm going to show you over here is more of a black box model. It's still kind of a gray box model in the sense that we put in some mathematical structure, like the one you can see here. What I've done here on the left-hand side is to just use the data to take the time derivative, but actually solving this equation, this partial differential equation, where the entire right-hand side has just been made into a neural network trained function. So over here, we have more mathematical structure. We have this negative diffusion, this stabilizing term. We have this partial derivative. We put a lot more mathematical structure. Over here on the right, we've removed more of that structure away. So it's still a gray box, but a lot less white. It's much more close to a black box model. So now if we train the data set on there using the exact same type of comparison, where over here we're comparing it with the withheld data, let's see what the function f looks like as a function of spatial position x for different time points. Once again, the yellow is the prediction and the dashed blue line is the truth. So you can see that it still does a pretty decent job. But there are some points where it doesn't quite agree, especially at these rapidly dynamical regions where you can see some areas where the waves are crashing into each other. And during these sections where you have high frequency modes and waves that merge and crash into each other, these types of shock events are not well captured under this model. So it's saying that it's not quite learning all the features that are present with the negative diffusion and the stabilizing fourth order term. All of those terms aren't quite being captured here because it's clearly missing some instances when there are shock waves that meet each other. And by the way, there's a couple of things under the hood that I'm doing with this training that I haven't fully covered yet. One concept is the concept of embedding. There's a very powerful tool called time delay embedding, where you're only not using the current time and the previous time to evaluate derivatives, but you're actually taking an embedding of many past histories of your data sets, combining them all together, so you're feeding your model more data that are connected through a time derivative over history. We're going to talk about time delay embedding next, but let's not worry so much about that, even though this concept of embedding does dramatically help even for a black box model to converge decently well. If you don't use time delay embedding, this model that you're seeing here is not going to be as good. It's actually going to be poorly predicting the true data. Embedding is covered next. Now, over here, back to our gray box model, we can now actually plot this converged function v that we used for the neural network from the gray box model. And it turns out it looks something like this. So this is just direct plotting of the function unknown function v as a function of f that the neural network block converged to. So remember in my demonstrations of the chemical rate law, we did the gray box, we used the concentration data set, we had our rate predicted from the neural network. We made a plot of that in the MATLAB code every single time. I showed you the actual concentration, transient comparison between the true data set, but then I actually plotted the actual converged neural network rate equation. And we said, oh, how close is that to the true solution? It's the same spirit right here. We're actually taking the neural network converged value of the unknown function v, essentially the weights of the Legendre polynomial, plugged it into the series, and boom, out came this function right here. And the yellow points, just like you see here, are the predicted points based upon the neural network. Now, this looks like a quadratic, a parabola. And that's great news because up here I wrote down the exact result. So the true solution of the Kuramoto-Sivashinsky equation is exactly f squared divided by 2. That is the nonlinear functionality of the unknown mystery function. So it turns out that indeed, using that gray box model, we do find 1/2 f squared. It's the equation of a parabola. And because we found the right functionality, of course, the yellow and the cyan dashed line are going to agree very well because we could just converge to the right term in the PDE. So you're just solving the same PDE twice. Of course, they agree very well. Now, this is an example where some of you watching may say, did you really need to use a neural network for this particular model? Probably not. You could have actually just done a regression least squares type regression to obtain your coefficients. Once you put it in the form of a Legendre Fourier basis expansion, finding those coefficients really could have done without the neural network. But I just wanted to show you one way in which you can find the weights using the gray box, which is what we covered in a previous lecture. Now, I'd like to move on to a different example, example number 2 in this video, that talks more about sparse regression and less about the neural network approach that we're talked about in this problem. So let's move on to that example next. In this example, which is a completely different example than the one we just talked about, is about fluid mechanics. The most famous equation in fluid mechanics is this one right here, the Navier-Stokes equations. What we have is a velocity vector, v, that has components x, y, and z in 3 dimensions, x and y in 2D. It's going to be a function of time as well. So on the left-hand side, we have a time derivative. We have this term right here, which is the turbulence term, v dot grad v. That's the term that creates chaos and nonlinear dynamics and tornadoes and turbulence and crazy things in fluid mechanics all happen because you have this specific nonlinear term. Now, this last term right here, I wrote it as 1 over Reynolds number, which tells you the balance of the viscosity over the inertial effects in the fluid. And this term at the very end is the divergence of the stress tensor sigma. That contains the viscous terms like the gradient of your velocity field and also contains the pressure field inside of your fluid for a Newtonian fluid. Now, in general, this stress tensor sigma has a very complicated relationship between sigma and the velocity and velocity gradients. But for the Newtonian fluid, this just contains the gradient in the velocity plus your pressure field. Now, we can actually solve this nonlinear partial differential equation for a 2D flow over a cylinder. So we have here is an object right here in dashed white line. This is a cylinder. It's sitting inside your fluid, and there is a uniform velocity field that's streaming past the cylinder. And we're doing this solution of this PDE on top at a Reynolds number of 100. So that's pretty high Reynolds number, which means that the inertial effects are very strong. Now you can see that what I'm showing here in color is the vorticity. Vorticity is the curl of your velocity field. It tells you how things are spinning. Curl, right? The vorticity of your velocity field. And this solution was obtained using the immerse boundary projection method by Professor Colonius's group at Caltech. And you can produce these beautiful color contour animations of the fluid field and the velocity, the vorticity streaming around the cylinder. You can see these von Karman vortex shedding coming out from the back of the wake of the cylinder. Now, going to, again, to what we're talking about in this class. Let's suppose that this measurement was all you had. Suppose that now you didn't even know that this came from the Navier-Stokes equations. Let's wave goodbye to the Navier-Stokes equations because we no longer know that this velocity field even came from that equation. Experimentally, you might be a geologist and you just measured some kind of flow happening at some point in the environment. And let's suppose you have some measurement of a velocity field, or you're measuring a glacial flow inside the Arctic. So you have measurements of the velocity field around some obstacle. Can you really just use this information of the velocity field to reconstruct a model of the Navier-Stokes equations? That's a question that's very interesting, actually a very active and current area of research. And it's also related to what we've been talking about. So one approach that people have adopted is to say, okay, expecting a computer to learn all of the entire state space of all the complicated connections is likely going to be very hard. So let's still put a lot of mathematical structure. One way to put mathematical structure is to pose the problem as shown here. We're going to have some velocity field, which is the model we want to generate. We're going to have a time derivative all the way on the left-hand side. And over here on the right, it's going to be some function of the vector field v. And if you think about what are the possible terms that we can even construct using a vector field v that obeys all the proper symmetries, then it turns out that you only get kind of set number of terms that are plausible, that obeys all the mathematical and physical symmetries inside the system. For example, you have the normal term v. You could have the square root of v squared times v. This whole thing is a vector quantity. You could have v dot grad v, that's an overall vector. This one is gradient of divergence of v, again a vector, and so on. You can get terms based upon symmetry arguments, the plausible terms that might describe the phenomena in this picture. Now, this is looking a lot more like sparse regression, because we can now build our library and see if our sparse regression will really pick up the correct terms. Now, the correct terms for the Navier-Stokes equations first is this viscosity term, Laplacian of v, right? That's in the Navier-Stokes equations. That's contained inside the stress tensor. This term over here is the turbulence term right there. So if the sparse regression could pick up this term and that term, then yeah, it means that out of all the possible candidate terms that could be present, it has successfully picked out the right terms. This again uses a lot of physical insight. We're constraining the entire search space to only these subset of terms that describe this super complicated vortex shedding problem at high Reynolds numbers. So we can pose the problem in a way that I showed you with the sparse regression. First, we can take measurements, which is data that you already have access to, in the form on the left-hand side. Now here I'm showing you measurements of the vorticity, which is the curl of the velocity field. The reason why we're measuring the vorticity instead of the velocity field is because there's this pressure field term inside that stress tensor, which becomes a Lagrange multiplier that you need to add because your fluid is incompressible. It gets kind of complicated. So if you take the curl of the Navier-Stokes equations, it turns out you can do this clever trick that makes your pressure field go away, and it makes your problem solution a little bit easier to obtain. So in any case, we're taking derivatives of the velocity field to get the curl, and so you have measurements of the time rate of change of your vorticity field as raw data measurements. So omega sub t, that's the partial time derivative of your vorticity field. Those are your measurements. Now, on the right-hand side over here, these are your candidate libraries. I just showed you all the terms that might possibly perhaps be contained inside of your library. So you can put those terms inside this gigantic matrix. And again, you know what those terms are, like the last lecture for the concentration and the rate law. You know what your library terms are. Okay, so this gigantic matrix you know. The notation I'm using here is the same notation that is contained in this paper right here that did a lot of really cool work on these types of sparse regression problems in fluid mechanics. Now, What I have here, u is the velocity along the x direction, v is the velocity along the y direction, and then omega are the vorticity. Each of these are partial derivative with respect to x, y, and so on. Now, over here, way on the right-hand side is your column vector of all of your weights, coefficients that contain how much of u do I need to take, how much of v do I need to take, how much of omega do I need to take, and so on. So it's taking weights of all these different terms that are possible inside your library and saying, okay, what's the best mapping to the measurements you see on the left-hand side based upon your pictures that you've taken from your velocity field. Now, this gigantic matrix I'm going to call theta. This is a Greek symbol, capital theta. And now this has turned into a sparse regression problem, just like I discussed last time. So we have is a unknown coefficient matrix, xc, which is a vector of all of your weights of the different terms inside your library. This first term on the right-hand side is the least squares with the 2 norm. I showed you that last time, what the definition of the L2 norm is. So it's taking least squares, right, the backslash operator, plus it's taking a sparsity term. Because once again, I'm stingy and I'm frugal. I don't want to carry around all these different terms in the library. I only want to carry the minimal set of terms that best fits the data. So I want the stingiest, most frugal possible model that still fits the data. That's the spirit behind this term. And this arg-min is saying, find me the argument of the thing that minimizes everything on the right-hand side. Okay, so you go through this process using the measurements. So once again, you know everything on the left-hand side, so you know this entire vector. You know everything inside this gigantic matrix, and now you're trying to obtain the coefficient vector xc. Okay, let's see how this performs. So first, what I'm plotting here is the truth. This is the Navier-Stokes equations in the vorticity description. So we have partial omega partial t plus these two terms are the v dot grad v. These are your turbulence terms. When you take the curl, it turns into these terms right here. So this is the term that produces turbulence, chaos, nonlinear dynamics, all of the wonderful things in fluid mechanics. Over here on the right-hand side, we have 0.01, which is equal to 1 over the Reynolds numbers. And what we have simulated is a Reynolds number of 100. So what we expect to get is 0.01, which is 1 divided by 100. Reynolds is 100 in our case, and therefore we have a viscous term right here, which is just 0.01 of the Laplacian of the vorticity. This is the truth. Let's see how close we get. First, if we do exactly what I showed you, where you construct a library containing the turbulence terms inside there, and you do sparse regression, out comes this solution right here, based upon the training set of flow around a 2D cylinder. It turns out that you get really close to the actual answer. Effectively, you get the right answer. You get negative, essentially 1 of u times omega x, and then minus 1 v times omega y. So you exactly get the turbulence terms you see right here. I just moved this over to the right-hand side over here, so that's why I have a negative sign out in front. But you exactly get this v dot grad v term in the Navier-Stokes equation. So you spot on capture the right terms in the Navier-Stokes for the inertial terms. Plus, you even get the viscous terms. You even get the right terms for the viscosity. So 0.01 Laplacian of omega, which is the sum of these two guys in xx and yy. Now, if you measure the metric of error, it gives you some value. That's how off this solution is from the true data set that you provided. We're going to use that number as a benchmark for a couple of different cases that I want to consider next. Now, out of curiosity, I was wondering, why is that v grad v term so special? There's entire classes on fluid mechanics that study the turbulence term. And that turbulence term, again, looks like this. And that's the term that you see in cyan here and here. When you take the curl, you're going to get these two terms present. And I wondered if the library was missing this term, what would it do? Obviously, if the library was missing this term, then it can't find these two terms that I drew in cyan, which came from the original library. So it has no way of obtaining those terms. But I thought, well, maybe that's doing a little bit too mean of a job. Let's supplement removing this, but instead adding gradients of V, gradients of the vorticity, and products of those two. So I'm still putting in gradient terms inside my library, but I'm not putting in a function times the gradient of that function anymore. I'm putting gradients of V, gradients of omega, and their products of each other. I wondered, can those terms alone compensate for the lack of my v.v term? So I'm using a different library now. I'm not using this top term. I'm putting terms that look like gradients of vorticity and my velocity and the products of those two. Let's see what happens. That's what I see right here. Once again, now case 2 is I have a library with only gradients of the velocity and their vorticity plus their products, terms that look like this. Okay? And I took the same data set. I used this new library containing these terms, did sparse regression, boom, out came this equation that you see on the right-hand side. Partial omega partial t equals all of this stuff over here. Basically, I don't get the right answer at all. I mean, if you look at the error all the way over here, you see that it's 10 to the 66, which is saying, oh my gosh, my data and my predicted model is so wrong that this, whatever I wrote here on the right-hand side is totally nonsensical. It does not at all explain or fit the data that I've provided. So it really struggled. And that taught me that terms that look like this cannot compensate for the turbulence term that's contained in the Navier-Stokes equations. There's no combination of grad V, grad omega, or their products that can ever replace a term that looks like the top equation, V dot grad V, which I found kind of interesting. And I said a step further. Okay, so then there's something very, very magical about a vector V that's being convected along as a wave. So this is a wave. So grad V in Fourier space gives you an IK V, and that's got a wave to it because IK terms give you waves. That's like sines and cosines, right? E to the IK gives you sines and cosines. And so we have our E to the IK, which is sines and cosines, being convected along. So you have waves, E to the IK, sines and cosines, being convected through V. So there's something special about the combination of waves being convected along that this term captures that these products and these two terms do not capture. So then I thought, okay, then let's try something else for case number 3. Let's suppose that I still don't have V dot grad V, but I have other terms that look like U squared grad V. So terms that are higher order in V and products of grad V, but not this quadratic. So this is a quadratic form, right? So I have V and grad V. That's like a parabola. That's got a quadratic term that's contained in the Navier-Stokes equation. This is more of like a cubic term. So it's V squared and another grad V. That's like more of a cubic term. So I said, let's try adding these higher order cubic terms without the quadratic terms, and can these terms compensate for the lack of a lower order quadratic term? So that's case number 3. I've put in these cubic terms, cubic nonlinearities that look something like that, and I wanted to see what we get. So case 3, is the library without the normal, quote, turbulence term, but with higher order terms present, terms that look something like this. Boom, sparse regression, and I get this. It's not very sparse, but I get this. Okay? So first thing, the error on the bottom right, 62. Now you look at this and say, oh, that's a pretty high number. Well, actually not really. Not really. When you think about something catastrophic like this, 10 to the 66, 62 is actually pretty decent. If the true solution was this, and case 1, which had all the library terms, gave you this equation, which was only 0.01 off, and that small little difference gave you an error of 18.7, this error of 62 ain't actually all that bad. So what this is telling me is that, interestingly, when you have these higher order terms present, for example, omega squared grad omega, boom, there's a term right there. Here it is. U squared grad omega, u v, so u in the x direction, u in the y direction, times the mixed derivative of omega. That's an even higher kind of term. But whenever you have these higher order terms present, it turns out you can actually, to a large extent, compensate for the lack of this usual turbulence v dot grad v term. That's at least what I'm finding in this preliminary kind of toy problem. And I found this so interesting that you can still produce a model, the one you're seeing in case 3. And I bet you if you actually solve this equation, you'd get a pretty good representation of that flow around a cylinder. It would probably work pretty well. I mean, given the error, pretty small, it has a shot of working pretty well. It's not 10 to the 66. Now, it's not clear whether this is generalizable. It's not clear, for example, if you change the Reynolds number, how much will this hold? If you change the size of the cylinder, how much is it going to hold? If you put boundaries, is it going to hold? So the transferability to different domains, different geometries, different Reynolds numbers is not guaranteed at all. But I still found it interesting that there is a chance that higher order terms like this, or even higher fourth order terms, could potentially compensate for the lack of a normal turbulence term. And if that is really true, that tells me that the Navier-Stokes equations is a special model, but not special for the reason that I used to think. It turns out that you can have other models that describe fluid flows in rivers and lakes and along mountains, but it just so happens that the Navier-Stokes equations is the sparsest possible model. What I found is that the Navier-Stokes equations is the sparsest model of fluid flow. I mean, think about it. If I said this model down here, model number 3, predicts the data pretty well and might actually, maybe, predict fluid flow down an incline or down a river, so let's all use this model. 99.9% of you said, get out of here. There's no way I'm going to type all this and carry this around all the time and do stability analysis and do all this stuff on this equation. There's no way. It's a cumbersome equation. It's got like 10 plus terms on the right-hand side. There's no way that people would actually adopt this model. And what's actually remarkable about the Navier-Stokes equations right here is that it's so simple. It's got only 1, 2, 3, 4 terms in the vorticity formulation. And that is actually one of, well, there's a lot of things that are special about the Navier-Stokes equations. But to me, after this exercise, what it taught me is that that's actually one of the very special things about the Navier-Stokes equations is that it's just so sparse. You got just 4 terms, you just carry it around in your pocket, and it ends up agreeing with so many different geometries. You can use the same equation for different geometries, different systems, different Reynolds number. As long as the continuum approximation is true, In other words, as long as your boundary confinement is not on the scale of a solvent molecule, where the continuum approximation breaks down so that you no longer have a well-defined density, velocity, temperature, pressure, energy inside that space, as long as you're bigger than that continuum, then you can always use this equation for a Newtonian fluid. That's actually kind of remarkable. And it taught me again, philosophically, there are so many different models that might work. This model down here may work. This may be a model that actually explains a lot of fluid mechanics, but no one would actually want to use it. So a model, the Navier-Stokes equation, is not really a law. You have a choice. You could use the Navier-Stokes equations, but there's a lot of assumptions, for example, in the Newtonian constitutive equation that we're relying upon, that we're assuming and taking for granted is true. And then out comes the Navier-Stokes equation, but it's a model. It doesn't have to be true. It's based upon assumptions that are built into the stress tensor, the continuum approximation, that then allow us to use this model in a useful way. But there's nothing special per se about that aspect. What's more special to me is the fact that it's sparse and it could be used in so many different contexts. It's very useful as a model. So anyway, those were just some of my random musings about this exercise, and I thought this was a nice example where we use sparse regression. And you have to be really careful about the terms you add to your library, because if you don't, like I said, if you kind of don't know the answer, it can be very misleading and challenging to know what your model is doing and how to discover other types of nonlinear models. Great, that's all I have. I hope that was fun. It was fun for me. It used a lot of principles from class and actual examples and concrete problems in research. And I will see you next time. Bye!